Yo, physics nerds. I'm going to make a quick video here to try to show you a concept. So what you're looking at here, let me back up a little so you can see it better. This is called Newton's Newton's cradle. Okay? So all it is equal massed steel bearings or ball bearings that are hanging by strings. Right? It's like a swing. So like if I take all these out of the way, not mess this up. Oops. I'll grab these. Ready? Watch. So it's just a swing. The thing is though, all of these masses, because they all have mass, let's call them masses, they're all lined up. So what this shows a good demonstration of is, well, a few things, right? When you pull one of these up, it has more gravitational potential energy, right? And when it's moving, it has kinetic energy. But there's another few things that are shown here, right? We know Newton's third law. Every action causes an equal and opposite reaction, right? And if you have a force on an object, it makes it accelerate. But there's another law, and it's called momentum. You've probably heard that word. Momentum is how fast something's going times how much mass it has. So it's mass times velocity, m times v. So there's a law called conservation of momentum, meaning momentum never just disappears, meaning like the amount of momentum you start with must be the amount of momentum you end with. Okay? So I'm going to show you a quick demonstration of the Newton's cradle running. So check this out. If I take one of the masses, bring it up here, watch what happens when I let it go and it knocks into the others. You notice how the energy is getting transferred through all of them? And you notice how I picked up one mass and only one is getting knocked off the other end? So now, eventually they come to a stop. Well, where's all the energy going? Well, actually, you're partially hearing some of the energy go missing, right? Some of the energy is getting wasted as sound. And if we were to get the temperature there, some of the energy is getting released as heat, right, from the friction of the masses hitting each other. And there's even a little friction with the wires here. So yeah, so if there was no such thing as loss of energy, these would keep running forever and ever, but we know that's not the case. Let's try this again, so make it a little more interesting. This time, you see how I'm grabbing two masses? Watch for this. When I grab two masses and let them go, check this out. Look at the other side. See? The mass in the middle is basically staying still, and it's two getting knocked off of both sides. So again, what this is showing is the law of conservation, meaning keep the same, and momentum, which is mass times velocity. So basically, the faster something's going, the more momentum it has, and the more mass it has, the more momentum it has. So basically, a little kid running really fast has the same momentum as a really big person walking slowly, all right? So let's do that one more time. So I'm going to increase the gravitational potential energy, and when I let it go, the kinetic energy increases, and the energy gets transferred back and forth through the marbles there. And the only reason why they start to slow down is because some energy is being wasted as heat and sound. One more time. We'll do it with, oh, wait, what about three? All right, check this. Let's see. So let's compare them. Let's do them. Ready? So one. See? Both sides. One gets knocked off. Let's do two again. See? Let's try three. Look carefully. Let's see what happens. Oh, three, 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 three. Haha, I messed it up. Let me try that a little bit better. Ready? Cool. So there you go. Basically, momentum stays the same. So basically, like if you roll a bowling ball into another bowling ball that has the same mass, one bowling ball should come to a total stop while the other one keeps going. All right, there you go. Conservation of momentum.